This is Design Safe Radio, where natural hazards researchers strive to make our society more resilient to everything nature throws at us.
So speaking of some of those elements, you got a lot of interesting things to change that tall wood building. From you didn't just take the 4 stories off the top. Now you're looking at some new technologies, some new design techniques. So for those who aren't experts in structural design or engineering, can you talk about things like those U-shaped flexural plates on the sides of the walls and some of those buckling restraint braces? Those are a couple of those things that you're looking at, and how they interact with rocking walls. And can you tell us about what your research team is looking to see with those two specifically?
Yeah, no, that's a great question. So we have 3 phases in the project, and one of the phases uses a structural system that you were mentioning, has the U-shaped flexural plates, or UFPs. I'll probably use that word a lot because that's what I'm more used to. But yeah, U-shaped flexural plates. And if you cut a clip, a paper clip, cut a chunk of that, and look at that little U, that's really what we're talking about in a bigger scale. And that in the walls, as the walls move and the walls rock back and forth, those UFPs can deform, and that's how we dissipate energy. So in our phase 1 of testing, where we have those walls, we have those energy dissipators at all the stories. So we call that distributed energy dissipation over the height of the building. And so that's one aspect. Those walls are post-tensioned. So not only do we have the energy dissipation, but as part of our resilient design, we want the walls to recenter after big earthquake. And I have a prop here. Let's see how that works.
Oh yeah.
Probably here. Which I don't know if you guys looking at this or hearing this podcast have seen these toys before, but these are mainly done so that you can push a button and the building goes down. But for us, it's really, you could push on the building, right, due to earthquake loads, for example, and due to the cables that are inside, or in our case, we have post-tensioning, the building recenters. That's very basic concept that we have for the post-tensioning rods that allow the building to recenter. So that's phase 1. U steel flexural plates, the little bottom of the clip. Phase 2. Phase 2 has what you mentioned, the buckling restraint braces at the ends. But there we're only putting them, they're still our energy dissipation mechanism, but it's only on the first story. So instead of distributed energy dissipation, we have concentrated energy dissipation on the first story. And that's really where the research question is, because as our buildings are tall and there's dynamics of the motions, can we have similar performance if we concentrate the energy dissipation versus if we distribute it? And so that's really why we have those 2 designs, is to assess impact of distributed versus concentrated energy dissipation.
So looking at, because I imagine there's pros and cons of both design philosophies. Of the distributed, you have less of a single point of failure, but it's also more construction time and more manufacturing time and materials, versus concentrated of, if you have one of them fail, then it's a big deal. But if it's able to handle the design loads, then it's less cost to construct and install and probably some other things. Right. But and sounds like overall, like that concept is kind of like a shock absorber on a car, right? It's just absorbing those bumps and then turning it into heat, or deforming a material rather than breaking things.
Yeah. So controlled damage, right? And that controlled damage in specific locations in the building we also call them sometimes structural fuses. Like you'd have, in a breaker box, you have a fuse. So, you can go and replace your fuse. All of these elements, yes, that's a goal as well, is after a big earthquake, they have some damage. The building is still functional, but we can go and replace those structural elements, those structural fuses.
Yeah, which is much easier to replace than an entire wall or the roof or
Right.
all the
Exactly.
windows in the building.
Exactly.
Yeah.
Yeah,
And
exactly.
we've been talking
Yeah.
a bit about here. I mean, in Eugene and where you're normally at in Corvallis, like, okay, what's going to happen to normal houses and apartment buildings and things like that when the Cascadia earthquake happens? And we're just our normal conversation over dinner with our my son's hockey team and parents were like, okay, like what is going to happen? Like some of our houses are going to be uninhabitable for a long time, and if you live in an older apartment building, a lot of the buildings downtown Eugene, even in the university, are not built to absorb energy and concentrate the damage. It's brick and concrete, and it's going to fall. So it's really good to hear that there's really smart people looking at stuff like this.
Yeah, and that's our goal, is to provide these solutions. We know that as a community, things are going to take time to change, right? There's always many other things, but at least we're going to provide solutions, hopefully are good solutions for the future here, sustainable and resilient.
Yeah, exactly. So you've talked about kind of the first couple of phases of this project. First looking at the UFPs and then the BRBs, and then the third phase is a bit more involved with adding some resilient steel frames. So how does this differ from the approach of those rocking walls and the UFPs?
Right. So one thing that this resilient steel frame does not have is the post-tensioning. So it does not have that self-centering capability there. But if I were to say, it's probably closer to traditional solutions that we may have seen. What I mean by that is there's steel moment frames, there's steel brace frames where you see the diagonal braces in the steel building going up, especially in earthquake regions, or even for wind loads. Here, this resilient frame is actually, it combines those two aspects, the moment frame with the brace. So it's a moment frame slash concentric brace frame. And what's new is that we are providing specific locations where there's energy dissipation. So in the brace, we provide energy dissipation at the ends with structural fuses. They're not UFPs, but they're slightly different design for yield links at the ends of the braces where yielding can happen. And then instead of, for example, in a typical brace frame that still takes the deformation, the brace absorbs the energy, and then you'd have to replace the whole brace. Here, you will only have to replace the yield links at the ends.
Okay. So they're
again,
just
that's a
slightly
structural fuse.
less stiff material than the rest of the brace, so that you design and control where the break is going to happen.
That we control where it can yield. So what's the elements that we can replace? Where are our structural fuses? So it would be a relatively small piece that you'd have to take off and put on.
Mm-hmm.
So that's one aspect. And on the beam to column connections, also we have yield links. Again, so those are structural fuses, but very concentrated structural fuses where the damage could occur, and that's what we replace. But by combining these two systems, the moment frame and the brace frame, we can also reduce the drifts. So even though there isn't post-tensioning, the design is such that the drifts are smaller. So with small residual drifts, people can still go back and resume their lives and then replace those structural fuses and get back smaller recovery times, which is the goal for the functional recovery.
So it sounds like
one more little detail on these frames. Sorry, Dan. One more little detail is that most of these frames built today have a lot of welding, and there's some challenges also with that, especially for repairs and recovery. Mm-hmm. And so a lot of the connections in this design have many bolts but that's because we can, again, take off parts, put in new parts. So it just makes it easier to repair if there is damage after a very, very big earthquake.
Yeah, that's a really good thing to hear, because I mean, anybody who's ever tried welding before, it's not a trivial thing to cut a piece out, to re-prepare it for welding, to weld it back in, especially if you're in a post damage event. You may not have power to weld, but a couple guys with a big impact driver to take out some bolts and put new bolts in, that's a lot more feasible.
Yeah.
After a really large earthquake event.
Exactly.
Thanks for listening to today's episode of Design Safe Radio. Be sure to like and subscribe on whatever platform you happen to be listening to this on. It really helps people find our show. Thanks to our amazing sponsors, the National Science Foundation and the NHERI Network Coordination Office, which is award number 2129782. Big thank you to Marty LaChance, our guest booker and topic researcher extraordinaire, and Raquel Ruiz, who is our video and audio editor. I'm your host and NHERI Facility Scheduling and Operations Coordinator, Dan Zahner. We'll see you in the next episode. Until then, stay resilient.